All right, today we're going to talk about energy stored in a magnetic field, as opposed to where we talked before about energy stored in an electric field. By now we have our four components to a circuit. We have our voltage, which here, let me alter this a little bit. Okay, we have our voltage, which is which is that symbol. Okay, we have our capacitor, okay, which has our charges in there, and we have our magnetic field going across. Okay, and the change in voltage on this guy is Q over C, right? Or Q equals CV. Our charge equals our capacitance times our voltage. Okay, we have a resistor. Okay, and our delta V is equal to the current times that resistor. And then finally we have our new thing, which is the inductor. Okay, and this has its own delta V, which is given by the inductance times the rate of change of the current. All right? Now, this inductor will have its own magnetic field, and it... Oh, and sorry, I need to put the... so L. Okay, we call it an L. And it has its own magnetic field coming in through like this. Essentially, it creates a magnetic dipole through the inductor. Okay, and with all of our magnetic fields being loops, okay, it goes through our inductor. Okay, the inductor is the magnetic field version of the capacitor. It stores energy into a magnetic field rather than storing it into an electric field. All right, so we are going to create a circuit here. All right, so we've got our voltage, and we have our resistor, and our inductor. Okay, and we've determined that as we do our voltage walk around our circuit here, we have this part here that's actually going to be a net positive for our voltage. Come along as long as the switch is closed. All right. So the switch is closed. We have a net voltage, net positive voltage here. We come around, we hit our resistor, and this gives us a voltage loss of IR. Okay, and then we have another back voltage from our inductance, which is a negative voltage. And as we go around any circuit, according to Kirchhoff, all those equal 0. Okay, that was our loop rule, that all of our voltages equal 0 as we go around any particular circuit. Well, I'm going to do something a little tricky here. And I'm going to, just work with me here, I'm going to multiply both sides of this equation by I. Okay, no, not the imaginary I. No, because we're not ready to blow minds that way. But just times the current. We'll multiply them all by the current. Okay. So what does that give us? That will give us, that'll give us IE. This will give us I squared R, right? And this gives us IL d I dt, and this will still equal 0 over here. Yes, Nick. You guys might see from this I squared R, or I times V, these are all terms of power. Okay, these are all of these produce a joule per second. Okay, as their final unit. Well, but what is this telling us? This IE would then be, this is the rate okay, this would be the rate of the rate at which we're adding energy to the circuit, right? Power is delta energy over delta time, right? d dt. That's our power. Well, if that's the power that this voltage is supplying, then it is increasing the energy of our circuit right here. Well, these guys are decreasing the energy of the circuit. IR becomes I squared R is going to be the rate at which we are losing energy of the system. Okay, what do we lose it to? We lose it to light or heat or whatever we're using the resistor to. Whatever we're using the resistor for. Okay, this one is the rate I don't want to call it stored in the inductor. I'm going to call it stored in the rate of energy stored in the magnetic field. This is the rate at which we are storing energy in the magnetic field. It's this over here, which would be a negative value from this. That if this is producing energy, it's going away here. It's getting sucked up to make this whole thing 0. All right. Well, we're going to call this then, this term, we're going to call this the potential energy. That's what it is. If we're turning all this energy, we're turning it into potential energy here in this loop. We're going to call this the potential energy stored in the inductor, the U sub L. Okay, but power isn't energy. Power is the rate at which the energy is changing, right? So this isn't U sub L. This is ddt of U sub L. And this is going to equal this term over here, our inductance, times our current, di dt. Yeah? Well, if they're both changing with respect to time, we can get rid of that, and we create a new differential equation. Okay, where our change in our potential energy is equal to LIDI. And you guys might see where this is going. Well, if we have a D here and we have a D here, then we can integrate both sides, yeah? So we're going to integrate both sides. Right, the L is a constant, so we take it out. This is easy. This is U. This is our change. Okay, our total change in our potential energy is going to equal, well, what's this going to be?
L I squared over 2.
1/2 Li squared. Does this look familiar to you guys? Say 1/2 mv squared, say 1/2 cv squared, say 1/2 Li squared, right? We have a lot of terms that deal with energy that actually have this this format to them, this 1/2 Li squared. Okay, this let me make sure I'm getting my train of thought here. Okay, so we're going to set this aside for a minute. Okay, here we have a solenoid. I'll zoom in a little bit here. Here's a solenoid, and from this we know that our magnetic field is equal to mu naught. In fact, if you've done your reading, which you may or may not have, but if you've done your reading, then we get our mu naught equal B equal to mu naught times the number of loops times the current. That's the strength of our magnetic field going through here. Okay. The other thing is, if you look at our, if you go back and look at the inductance a little bit in the book, our inductor is equal to mu naught again, n squared times essentially the volume of the solenoid. So the cross-sectional area times the length. Okay, that's going to be the inductance. That's how you calculate the inductance of the material when you have given these properties. Okay, we're going to convert this. I'm going to find out what this is for I. Okay, so I is going to equal B over mu naught n. And we're going to take these guys and plug them into this down here. So we're going to get our potential energy equals one half L times I squared. All right, and we have some things that are going to cancel here. The n squareds are going to cancel. Okay, one of our mu naughts will cancel. Okay, and so we wind up with our energy equals 1/2 B squared over mu naught A times L, and this winds up being the energy stored in a solenoid. Okay, so whenever we have a solenoid, whenever we have the situation that there's energy stored in this field, okay, and it equals this. Well, what's that?
So the number of turns doesn't have the effect?
It doesn't matter. Right. Okay. Now, however, and we've talked about this a little bit before with our electricity, that we're going to look at the energy density okay, this is we're going to calculate the energy density of our magnetic field. If I'm running out of space here. Okay, the energy density of our magnetic field. Okay, well, if this is volume, right? Well, density is going to be our energy per unit volume. So if we divide by AL, sorry, that should be lowercase l. Don't want to confuse you with inductance. That our energy density is given by a lowercase u lowercase u divided by that volume, which winds up equaling 1/2 b squared over mu naught, which is kind of interesting considering when we calculated our energy density of our electric field, we got that. Okay, and so there's a real similarity there between this and this one. All right, so let's take a look at this again. Where this winds up is we have our circuit here, and as we go around the loop, we have our voltage. Either we're increasing voltage or we're decreasing voltage. But if we multiply by the current, then now all of a sudden we're talking about the rate of the rate of energy distribution. Either we're adding energy to the system or we're taking it away somehow. Okay, where the voltage is our source of our energy for our circuit. This is where our energy dissipates to when we're running something. Okay, and if we have an inductor on there, we're storing that energy as potential energy in the magnetic field. From that, we can calculate the potential energy that is stored is 1/2 Li, okay, where it's our inductance times the current squared. Okay. And then from that, we get here to our energy density, which is 1/2 of the magnetic field over the permittivity of free space. All right, pretty abstract right there. Okay, but this is going to help you do some of the problems for this assignment, and it will come more into focus with the next lecture, which is our oscillations in an LC circuit, or we'll wrap it all up together. So